Hello all, welcome to my YouTube video. My name is Kushi S from Sri Venkateshwara College of Engineering. In this video, I will be discussing about cloud cryptography. I am very excited to share my knowledge with everyone. Hope it will be informative and helpful to all. I will walk through the introduction, working of cloud cryptography, overview of cryptographic techniques which includes symmetric key cryptography, asymmetric key cryptography, hash functions, digital signatures, key management, and access control mechanisms. I will also discuss about data protection, cloud cryptography protocols and standards, cloud cryptography applications, homomorphic encryption, challenges of cloud cryptography, benefits of cloud cryptography best practices, cloud cryptography tools and technologies. Without further delay, let's get started. Cloud cryptography is encryption that safeguards data stored within the cloud. It is the use of cryptographic techniques to secure data that is stored, processed, and transmitted in cloud computing environments. Several measures are being placed within cloud cryptography, which adds a strong layer of protection to secure data to avoid being breached, hacked, or affected by malware. Any data hosted by cloud providers are secured with encryption, permitting users to access shared cloud services securely and conveniently. Cloud cryptography secures sensitive data without delaying the delivery of information. It involves encryption, key management, and access control mechanisms to protect data in the cloud. The goal is to ensure the data is protected from unauthorized access, theft, and other types of attacks. There are several types of cloud cryptography techniques, including symmetric key cryptography, asymmetric key cryptography, and homomorphic encryption. Cloud cryptography is essential for ensuring the security of data in the cloud and is becoming increasingly important as more businesses and individuals rely on cloud computing for their data storage and processing needs. Now, we know what is cloud cryptography. So, let's move forward and understand the working of cloud cryptography. Cloud cryptography is based on encryption, in which computers and algorithms are utilized to scramble text into ciphertext. This ciphertext can then be converted into plain text through an encryption key by decoding it with a series of bits. The encryption of data can take place in one of the following ways. First one is pre-encrypted data, which is synced with the cloud. There is a software accessible to pre-encrypt it before information gets to the cloud, making it impossible to read for anyone who tries to hack it. Second one is end-to-end encryption. Senders and receivers send messages whereby they are the only ones who can read them. Third one is file encryption. File encryption occurs when at rest. Data is encrypted so that if an unauthorized person tries to intercept a file, they will not be able to access the data it holds. Fourth one is full disk encryption. When any files are saved on an external drive, they will be automatically encrypted. This is the key method to secure hard drives on computers. As we are now familiar with the working of cloud cryptography, let's move further and understand the various cryptographic techniques. Cryptography is the practice of securing information by transforming it into an unreadable form, called ciphertext, using mathematical algorithms. Cryptographic techniques are essential in ensuring the confidentiality, integrity, and authenticity of data. Some of the most common cryptographic techniques are symmetric key cryptography, asymmetric key cryptography, hash functions, digital signatures, key management, and access control mechanisms. Overall, cryptographic techniques are critical in ensuring the security and privacy of data in various applications and systems. The choice of cryptographic technique depends on the specific security requirements and the nature of the data being protected. Now, let's deep dive into each of the cryptographic techniques. First technique is symmetric key cryptography, also known as secret key cryptography. Is a cryptographic technique that involves the use of a single key for both encryption and decryption of data. The same key is being used by both the sender and receiver of the data, which makes symmetric key cryptography a simple and efficient technique for encrypting and decrypting the data. The process of symmetric key cryptography involves the following steps. Step 1. Encryption. The sender encrypts the plain text using the shared key to generate ciphertext. The encryption process typically involves the use of an encryption algorithm such as Advanced Encryption Standard, Data Encryption Standard, or DDES. Step 2. Transmission. The sender transmits the ciphertext to the receiver over a secure or insecure channel. Step 3. Decryption. The receiver decrypts the ciphertext using the same shared key to recover the original plain text. Symmetric key cryptography has several advantages. It is faster than asymmetric key cryptography because it uses a single key for encryption and decryption. It is efficient and requires less computational resources than asymmetric key cryptography. Symmetric key cryptography provides strong security if the key is kept secret. However, the key must be securely shared between the sender and receiver. It is compatible with a wide range of devices and platforms. However, symmetric key cryptography also has some disadvantages, like key management. The secure distribution and management of the shared key can be a challenge, particularly when multiple users need to access the same data. Lack of scalability. Symmetric key cryptography can be challenging to scale to larger networks or systems. Overall, symmetric key cryptography is a fundamental cryptographic technique that is widely used in various applications, including secure communications, data storage, and authentication. The second technique is asymmetric key cryptography, also known as public key cryptography. Is a cryptographic technique that uses a pair of keys. One is public and one is private for encryption and decryption. The public key can be shared freely while the private key is kept secret by the owner. Asymmetric key cryptography provides several advantages over symmetric key cryptography, including enhanced security and flexibility. The process of asymmetric key cryptography involves the following steps. Step 1 is key generation. The user generates a pair of keys. One is public and one is private using a secure algorithm. Step 2 is encryption. The sender uses the recipient's public key to encrypt the plain text and generate ciphertext. Step 3 is transmission. The sender transmits the ciphertext to the receiver over a secure or insecure channel. Step 4 is decryption. The receiver uses their private key to decrypt the ciphertext and recover the original plain text. Asymmetric key cryptography is also used for creating digital signatures, which are used to authenticate the origin and integrity of a message. The sender uses their private key to create a digital signature, and the recipient uses the sender's public key to verify the signature. Asymmetric key cryptography has several advantages. It provides enhanced security compared to symmetric key cryptography, as the private key is kept secret by the owner. Asymmetric key cryptography is more flexible than symmetric key cryptography because it enables the secure communication between multiple users without the need for a shared key. It also enables the creation of digital signatures, which are widely used for authentication and non-repudiation. However, asymmetric key cryptography has also some disadvantages. It is computationally more complex than symmetric key cryptography, which can make it slower and less efficient. Asymmetric key cryptography also requires secure key management to ensure that private keys are kept secret and public keys are distributed securely. The third technique is hash functions. A hash function is a cryptographic technique that takes an input or message of arbitrary size and generates a fixed size output known as a hash, digest, or fingerprint. The hash function transforms the input data into a string of bits or bytes that represents a unique digital fingerprint of the original input. Hash functions have several important properties. The first one is deterministic. The same input data always produces the same hash output. Second one is one-way. It is practically impossible to reverse engineer the original input data from the hash output. The third one is collision resistant. It is computationally infeasible to find two different input messages that produce the same hash output. Hash functions have numerous applications in cryptography. Hash functions are used to ensure data integrity by generating a unique hash of the original data, which can be compared with the hash of the received data to check if it has been tampered with or corrupted. Hash functions are used in conjunction with asymmetric key cryptography to create digital signatures which provide authentication and non-repudiation. Hash functions are used to store passwords securely by generating a hash of the password, which is stored instead of the actual password. When a user enters their password, it is hashed and compared with a stored hash to authenticate the user. Some common used hash functions include MD5, SHA1, SHA2, and SHA3. However, due to advancements in cryptanalysis, some of these hash functions have become vulnerable to attacks, and newer hash functions such as SHA3 are recommended for new applications. The fourth technique is digital signatures. It is a cryptographic technique used to provide authentication, integrity, and non-repudiation of electronic documents, messages, and transactions. A digital signature is created using a combination of asymmetric key cryptography and hash functions. The process of creating a digital signature involves the following steps. Step 1 is hashing. The sender computes a hash of the message or document using a secure hash function. Step 2 is signing. The sender uses the private key to sign the hash of the message or document, which creates a digital signature. Step 3 is verification. The receiver uses the sender's public key to verify the digital signature. The receiver first computes the hash of the message or document and then uses the sender's public key to decrypt the digital signature. If the decrypted value matches the hash of the message or document, then the digital signature is considered valid. Digital signatures have several important properties, including authentication, integrity, and non-repudiation. The digital signature provides authentication of the sender's identity, as it can only be created using the sender's private key. The digital signature ensures the integrity of the message or document, as any modifications to the original message or document would result in different hash value and thus an invalid signature. The digital signature provides non-repudiation, as the sender cannot deny having signed the message or document. Digital signatures have numerous applications in various fields, including electronic commerce, legal contracts, and government documents. They provide a secure and reliable way of verifying the authenticity of electronic documents and messages and are widely used for online transactions and communications. However, digital signatures also have some limitations, such as the need for security key management and the possibility of attacks such as key compromise or impersonation. Careful implementation and management of digital signatures is necessary to ensure their security and effectiveness. The fifth cryptographic technique is key management. It refers to the process of generating, storing, distributing, and revoking cryptographic keys in a secure and effective manner. Key management is a critical component of cryptography as the security of cryptographic system depends heavily on the proper management of cryptographic keys. The key management process typically involves the following steps. Step 1 is key generation. Cryptographic keys are generated using a secure random number generator or a key derivation function. The keys must be sufficient length and complexity to resist attacks. Step 2 is key storage. Cryptographic keys must be stored securely to prevent unauthorized access or theft. Various key storage mechanisms are available, including hardware security modules, smart cards, and software-based key stores. Step 3 is key distribution. Cryptographic keys must be distributed securely to the intended recipients. This can be done using secure channels such as secure messaging, secure file transfer, or secure key exchange protocols. Step 4 is key revocation. Cryptographic keys must be revoked when they are no longer needed or when they are compromised. Key revocation can be done using certificate revocation lists, online certification status portal, or other mechanisms. Proper key management is essential to ensure the security and effectiveness of cryptographic systems. Failure to properly manage cryptographic keys can result in key compromise, unauthorized access, and data breaches. Some of the key management best practices include use of strong cryptographic algorithms and keys, regular key rotation to minimize the risk of key compromise, use of secure key storage mechanisms such as HSMs, use of secure key exchange protocols such as transport layer security and secure shell, implementation of key backup and recovery mechanisms. Overall, effective key management is a critical aspect of modern cryptography and is essential to ensure the confidentiality, integrity, and availability of data and systems. The sixth technique is access control mechanisms. They are security measures implemented to control and manage access to resources and data in a system or organization. Access control mechanisms ensures that only authorized users can access specific resources, data, or functionalities while preventing unauthorized access, modification, or destruction. Now let's discuss about types of access control mechanisms. There are totally 4 types of access control mechanisms. Mandatory access control. This system is a security model that uses labels to control access to resources based on security clearance levels. Discretionary access control. This system is a security model that allows the owner of a resource to control access to the resources based on access control lists. Role-based access control. This system is a security model that assigns access privileges to users based on their roles and responsibilities. Attribute-based access control. This system is a security model that uses attributes to control access to resources. Attributes are characteristics or properties associated with a user or a resource such as age, location, job title, or security clearance level. Access control mechanisms are essential for ensuring the security and confidentiality of sensitive data and resources. Properly implementing and managing access control mechanisms requires careful planning and consideration of organizations' security policies, user roles, and access requirements. Access control mechanisms must also be regularly reviewed and updated to address evolving security threats and vulnerabilities. Now, we have understood about all the cryptographic techniques with its properties, advantages, and disadvantages. Let's understand more on data protection. Data in transit and data at rest are 2 important aspects of data protection in cloud cryptography. Here's a brief overview of each. Data in transit refers to the data that is being transmitted over a network or between different systems. In cloud cryptography, data in transit must be encrypted to prevent interception or eavesdropping by unauthorized third parties. This is typically achieved by using encryption protocols such as SSL or TLS or IPsec. When data is transmitted over the internet or other public networks, it's important to use strong encryption and secure protocols to prevent unauthorized access. Additionally, cloud providers should use secure transport mechanisms and ensure that data is encrypted both in transit and at rest. Data at rest refers to the data that is stored on disk or other storage devices. In cloud cryptography, data at rest must also be encrypted to prevent unauthorized access if the storage device is stolen or compromised. Encryption of data at rest can be achieved using various techniques such as disk encryption, file encryption, or database encryption. Cloud providers should also implement access controls to ensure that only authorized users can access the data stored in the cloud. This can involve using encryption keys and access policies to ensure that data is protected both in transit and at rest. Next, we will go through the cloud cryptography protocols and standards. Cloud cryptography protocols and standards are essential for ensuring the security of data and resources in cloud environments. Some of the most commonly used cloud cryptography protocols and standards include Transport Layer Security Cryptographic Protocol used to secure communication over the Internet. TLS ensures that data transmitted between clients and servers is encrypted and authenticated, preventing unauthorized access and tampering. Secure Sockets Layer is a cryptographic protocol used to establish secure communication between clients and servers. SSL provides authentication, confidentiality, and integrity of data transmitted over the Internet. Advanced Encryption Standard is a symmetric key encryption algorithm used to encrypt and decrypt data. AES is widely used in cloud cryptography to protect data in transit and at rest. RSA is an asymmetric key encryption algorithm used to secure communication and data exchange. RSA is commonly used in cloud cryptography to establish secure channels between clients and servers. Key Management Interoperability Protocol is a standard protocol used for managing cryptographic keys in cloud environments. KMIP provides a framework for exchanging key management information between cloud services and clients. Security Assertion Markup Language, an XML-based standard protocol, is used for exchanging authentication and authorization data between different systems. SAML is commonly used in cloud computing environments to establish single sign-on capabilities. OpenID Connect is an identity layer protocol based on the OAuth 2.0 framework. OIDC is commonly used in cloud environments to provide SSO capabilities and secure authentication and authorization. Now, let's move to cloud cryptography applications. Cloud cryptography applications are essential for ensuring the confidentiality, integrity, and availability of data and resources in cloud environments. Some of the most commonly used cloud cryptography applications include data encryption, secure data sharing, secure data storage, and secure data processing. Now, let's discuss about homomorphic encryption. Homomorphic encryption is a type of encryption that allows computations to be performed on encrypted data without first decrypting it. This means that the data can be processed and analyzed without exposing the underlying data to anyone, even those who have access to the encrypted data. There are two main types of homomorphic encryption, namely fully homomorphic encryption and partially homomorphic encryption. Fully homomorphic encryption allows for arbitrary computations to be performed on encrypted data, including addition, multiplication, and comparison operations. This is the most powerful form of homomorphic encryption, but also the most computationally intensive and complex to implement. Partially homomorphic encryption, on the other hand, allows for computations of a specific type, such as either addition or multiplication, to be performed on encrypted data. Homomorphic encryption has many potential applications in fields such as healthcare, finance, and cloud computing. For example, homomorphic encryption could be used to enable secure data analysis and processing in cloud environments without revealing sensitive data to cloud service providers. It could also be used to enable secure computation on data stored in untrusted or potentially compromised systems. While homomorphic encryption is still an active area of research, it has the potential to revolutionize the way we think about data privacy and security and open up new possibilities for secure data sharing and analysis. Cloud cryptography offers many benefits for organizations, including improved security, reduced costs, and increased flexibility. However, there are also several challenges associated with cloud cryptography that must be addressed to ensure the security and privacy of data. Now, let's discuss some common challenges of cloud cryptography and how to overcome them. Key management. One of the biggest challenges of cloud cryptography is key management. Managing keys for large amounts of data can be difficult and time consuming. And if keys are lost or compromised, data can be lost or accessed by unauthorized parties. To overcome this challenge, organizations should implement strong key management practices such as regular key rotation, secure key storage, and the use of hardware security models to protect keys. Compliance. Many organizations are subject to regulatory requirements that dedicate how data must be protected and stored. Cloud cryptography can make compliance more difficult because data is stored outside of the organization's physical control. To overcome this challenge, organizations should choose cloud providers that have implemented strong security measures and can demonstrate compliance with relevant regulations. Performance. Encrypting and decrypting large amounts of data can be resource intensive and can impact system performance. To overcome this challenge, organizations should carefully choose encryption algorithms that balance security and performance. Additionally, cloud providers should implement hardware acceleration and other performance optimizations to minimize the impact of encryption on system performance. Data migration. Moving data between different cloud providers or between the cloud and on-premises environments can be challenging when encryption is used. To overcome this challenge, organizations should carefully plan data migration and ensure that encryption keys can be easily migrated with the data. Vendor lock-in. Some cloud providers may use proprietary encryption technologies or key management systems, which can make it difficult to switch providers. To overcome this challenge, organizations should choose cloud providers that use open standards for encryption and key management. Cloud cryptography offers several benefits to organizations looking to secure their data and applications in the cloud. Some of the key benefits of cloud cryptography are improved security, scalability, cost savings, flexibility, and improved compliance. These benefits make cloud cryptography an attractive option for organizations looking to secure their data and applications in the cloud. Moving forward, let's see what are the best practices of cloud cryptography. Use strong cryptographic algorithms, use appropriate key management, implement access control mechanisms, secure data transmission, regularly monitor and audit cloud services, use multi-factor authentication, regularly review and update security measures, conduct regular security training. Proper implementation and use of cloud cryptography best practices and recommendations are critical for ensuring the security and privacy of data and resources in cloud environments. It is important to adopt a risk-based approach to cloud security and regularly assess and update security measures to address evolving security threats and vulnerabilities. Moving forward, let's know the tools and technologies of cloud cryptography. There are many cloud cryptography tools and technologies available to help secure data and resources in cloud environments. Some of the most commonly used tools and technologies are AWS Key Management Service. AWS KMS is a fully managed service that allows you to create and manage cryptographic keys used for data encryption, decryption, and other cryptographic operations in AWS. Google Cloud Key Management Service. Google Cloud KMS is a cloud-based service that allows you to create and manage cryptographic keys used for data encryption, decryption, and other cryptographic operations in Google Cloud. Microsoft Azure Key Vault. Microsoft Azure Key Vault is a cloud-based service that allows you to store and manage cryptographic keys, certificates, and other secrets used for data encryption, decryption, and other cryptographic operations in Azure. HashiCorp Vault. HashiCorp Vault is an open-source tool that allows you to store and manage cryptographic keys, passwords, and other secrets used for data encryption, decryption, and other cryptographic operations in cloud environments. OpenSSL. OpenSSL is an open-source toolkit that provides support for SSL or TLS protocols, cryptographic algorithms, and other security-related functions in cloud environments. Cloudflare. Cloudflare is a cloud-based service that provides protection against DDoS attacks, secure data transmission, and other security-related functions in cloud environments. Fortinet. Fortinet is a cloud-based service that provides advanced threat detection, secure data transmission, and other security-related functions in cloud environments. These tools and technologies can help you implement strong cryptographic protocols and standards, manage cryptographic keys, and protect data and resources in cloud environments. It is important to select the appropriate cloud cryptography tools and technologies based on the specific security requirements of the cloud environment and to regularly review and update security measures to address evolving security threats and vulnerabilities. By this, we came to the end of the video. Hope you all liked it. Thanks for watching. Please like, share, and subscribe my video.